So for those of you who, I'm going to have to pause that in a minute. So those of you who weren't here yesterday, this is something new I'm trying to see if it helps. These are more just check-ins, making sure we're understanding what we did the previous day. So all of them are going to be real short, try to, few things we can do, just check in and see. And after that, we'll go over it. Now, for the most part, I'm not going to try to hunt y'all down for the days you missed, okay? So previously, for those of you who weren't here, I'm just put N-A for it. We're not going to try to go back. Not because I don't want to, it's more you're trying to have to find time in the day to come answer a 5 little question quiz. And again, unlike yesterday, this is 5 points. I'm not going to be stressing over the 5-point quiz, okay? So again, it's just re-emphasizing what we did yesterday. Now, also with those, if you were absent the day of the notes, I still want you to try them, but it's not going to be detrimental because that's not on you, okay? Now, what we're looking at today, 5.21 is property of rational exponents. We have this entire list here. Really, property of the exponents. This is stuff we've been doing and you've done before. Our product of powers. If we multiply like bases, we add the exponents. We've done that before. Power of a power. Whenever we have a power of a power, we did this the other day, the powers multiply. So 3 to the 5/2 squared, 5/2 times 2 is 5. We can simplify from there. Powers of powers multiply. Power of a product. If we have two things being multiplied together inside of parentheses, the powers is applied to both. This is not addition, just 2a to the third, 2 is to the third, a is to the third. We apply it to both. Negative exponents, a to the negative m. We take it from the top to the bottom, because I don't think we've covered anything that we haven't used before. These are just going back over these properties. Our favorite exponent property is a zero exponent property. Anything to the 0 power is 1, except for what? 0. We can't have 0 to the 0 power. It just doesn't work. Anything to the 0 power is 1. Quotient power, kind of like product power. If we divide like bases, we subtract the exponents. And power of a quotient, if we have two things being divided to an exponent, we apply it to both. And we can go from one to the other. These are just our properties of exponents. You've had them before. You've seen them before at Algebra 1, probably in 8th grade. We've had them in some way, shape, or form. Probably not all listed at once and thrown at you all at once, but we've done these. Now, this is the first thing that we have. Simplified form. And we've danced around this a little bit, but for us to determine or say something is in simplified form, we have 3 main statements we have to satisfy or have to be true. The first one, no radicands or radicals have perfect int powers as factors other than 1. To clarify, as soon as I started writing it, our answer can't be the square root of 4. Because what is the square root of 4? 2. If it can be simplified, we need 2. No radicands can have perfect int powers as factors other than 1. So we phrase it this way because we can't have the square root of 4 as our part of our final answer. I can't leave it as the cubed root of 8. If we can take out those perfect squares, those perfect factors out, we need to. And out of these 3, that is probably the more confusing one out of the group, because the others kind of make sense, just from the wording of them. The second one, no radicands can contain fractions. I can't have the square root of 2/7. I can't have a fraction inside of a radical. and no radicals or radicands can appear in the denominator of a fraction. We can't have 1 over the square root of 2. I'm just using square roots because they're kind of easy to picture. A little bit easier to write since we're not having to put the index. Yes? So fractions and, yeah, they kind of put each other together. And it's kind of distinguishing the fact that this here, because 2 and 3 kind of do seem similar, 1 over the square root of 2, inside the radicand, that does show up in 1 over the square root of 2, there is not a fraction in the radical. That's square root, which satisfies 2, but 3 is saying specifically we can't have it in the bottom. Now, the only reasoning behind number 3 that I have come to, and I think most teachers or kind of most mathematicians have come to, is we don't want to divide by an irrational number. Because square root of 2 is 1 point, and it goes on and on and on and on. So we just try to avoid doing that. Because really, this here, and we'll get into it, is actually the square root of 2 over 2. That's the acceptable form of this. They are the same, exact same value. But we don't want the radical in the bottom of the fraction. So we get this here. Yes? So with some of these, it just means we can't have, we need to simplify in simplest form. Now, for the most part, there is some of this that really comes into play and can be a little more confusing. We'll get to it probably at the end of the year after the chapter test, just because of time's sake or how the days fall. This is our last chapter. So, what we're looking at is simplifying each expression. The first one's kind of nice. 7 to the 1/4 times 7 to the 1/2. If the bases are the same, we add the exponents. So we're saying 7 to the 1/4 plus 1/2. Now, unfortunately, the calculator will throw it, or it will give you an answer if you put 7 to the 1/4 plus 1/2 in it, but it gives you a decimal. But really, what are we trying to do? We're just simplifying. We're not finding a value. We're just trying to get it in simplest form. We want one base here. But we can do part of it in the calculator. Because what are we trying to add? 1/4 and? Which is? So in simplified form, this is 7 to the 3/4. We're trying to get it in simplest terms. As simple as we can get. That's it. I mean, if we wanted to, we could rewrite it as a radical, that it would be the 4th root of 7 to the 3rd, which I think would be the 4th root of 7 to the 3rd, 243, 343. That's not any simpler than this here. We're done. Questions on this here? Let's look at the next one. 6 to the 1/2 times 4 to the 1/3 to the 2nd power. Well, our 6 and 4 are simplified as they get. I mean, we can't multiply them together like we did with A, but we do have them both to the power of 2, yes? Powers of powers, multiply. So what we're going to say is that I have 6 to the 1/2 times 2 times 4 to the 1/3 times 2. Okay, that's what I thought. All right. What's our 1/2 times 2? 1. Yeah, because it's 2 over 2, which is 1, which is just 6. 1/3 times 2 is 2/3. I kind of jumped ahead of myself. Questions on how we got to this here? We ready for the next step? Yes? That's it. I mean, there are ways we can take it further than this, because 4 is technically 2 squared. And we could rewrite it doing that, and that's part of the reason, if you notice I grabbed the textbook, is to seeing how far they would take it. But here, we're saying this is it, as far as we have to go. Questions on this here? Let's look at the next one. 4 to the 5th times 3 to the 5th, all to the negative 1/5. That's kind of nice. Both of them are to the same exponent, yes? Powers of powers multiply, yes? Well, we can go the other direction, can't we? Because if they both have the same exponent, can I also take it away? Yeah. We can apply it, we can take it away. Because again, we want this as simplified as possible. Now, in the closest in the middle, we have what? 4 times 3. 4 times 3 is 12, isn't it? Because they both have the same exponent. That's the only reason we did that. Since they're both to the exponent of 5, we can pull it out. 4 times 3 is 12. Might need that one. Questions on how we got to this here? Now we say powers of powers do what? Multiply. Now we could take this one at a time. We could first say our 12 to the 1st to the 5th, 1 times 5 is 5, yes? But we're also multiplying all the way out. Doesn't matter how far we go. So really we have 12 to the 5 times negative 1/5. If I wanted to, I could have said 12 to the 1 times 5 times negative 1/5. Questions? Very good. Now, in some ways, I'm going to steal this term from a student. They were talking more about the trig, but I think it applies here. This seems less like math and more like cheating. In some ways, it doesn't feel like we're doing mathematical steps. It feels like we're tearing it apart, putting it together, just doing weird things. Because at this point, we are using the power or the exponent properties, yes? But up to this point, you've used a formula, used a property, we plugged stuff into it and used it, yes? We haven't plugged a thing in. We're pulling it apart, doing what we want with it. It's almost like playing with Play-Doh, in a sense. And we kind of see that in some ways. It's a little weird, but it does work. Here, 1 times 5 is, times negative 1/5 is negative 1. I mean, in a calculator, I could have done 1 times 5 times negative 1/5. Let it do it for us. Questions on how we got this here? If the exponent's negative, to make it positive, we move it from the top of the fraction to the bottom. That's it. We flip it. Yes. And if it does work out to give us a nice number, we can plug it in. But again, for the most part, what we're doing with this here is less about solving and more just utilizing these properties of exponents, okay? Questions on this here? Some of the stuff we'll do tomorrow you'll like even better. Use the properties of rational exponents to simplify each expression. So our next one is 5 over 5 to the 1/3. And there's different ways we can get at this. But the issue with this here is the 5 to the 1/3 in the bottom of the fraction. And the reason for it is because our 5 to the 1/3 is essentially saying as a radical. Yeah. Is that we have the cubed root of 5. That's all it's saying. We can't have radicals in the bottom of the fraction. We can't have these fractional exponents in the bottom of the fraction. But if we look at the problem that we have, 5 over 5 to the 1/3. We are dividing like bases, yes? If you divide like bases, we can subtract the exponents. So, 5. Now 1/3 is on bottom, yes? What's the number on top? As our 5 on top is 1. As if the exponent's not listed, it's understood to be 1. So really we're saying that this is 5 to the first minus 1/3. So we're really at this point looking at 1 minus 1/3. And 1 minus 1/3 is 2/3. Now we could do the 1 minus 1/3 in the calculator. It would give us our answer. We stick it back as its exponent. Questions on this here? We don't have a denominator anymore, so fractions are no more. We don't have to worry about them at all. And it works. The exponent's positive, so we're good there too. Questions on D? E. 42 to the 1/3 over 6 to the 1/3 squared, yes? Is 42 and 6 divisible? Can we divide 42 by 6? Yeah. So there's two reasons. One, 6 to the 1/3, just like 5 to the 1/3. We can't leave it there. We can't have that fractional exponent. So we've got to go about finding ways to get rid of it. Unlike the last one, the bases aren't the same. Top and bottom aren't the same. But they are both to the same power, yes? Like we did previously with 5 and 5. What I can do is say that this is the same as 42 over 6 to the 1/3 squared. Now again, this is only helpful if both exponents here, 42 and 6, have the same, and they are divisible. Well, what is 42 over 6? Now again, our big issue that we had was having a fraction within the fractional exponent. Do we have a fraction anymore? No, so it doesn't matter anymore. Now we just need to get rid of all these parentheses. Again, they're powers of powers, yes? So we're really looking at 7 to the 1/3 times 2, which is 7 to the questions on this here? Would y'all say this is oddly simple and oddly complex all at the same time? So again, if something doesn't make sense, ask. Ask. 2 to the 3/4 times 2 to the 1/2. Bases are the same, so we add the exponents. Two to the 3/4 plus 1/2. So we're doing 3/4 plus 1/2. Maybe a little bit bigger. 2 to the 5/4. Yep. Because 3/4 plus 1/2. 3/4 plus. We would need another fourth. So we would need 1/4 to add to 3/4. So our 1/2 is actually 2/4. So it's going a little bit past.
Well, I knew that 1/2 was 2/4, but I thought it just went to
Yeah, because
all on top of each other and just make one. It was like quarters.
almost. Yeah, because our 2/4, yeah, the same, or if we had 1. So if we said 3/4 plus 1, then we'd add 4/4 to it.
Oh, okay.
Any other questions on 1? 2, 3 over 3 to the 1/4. 3 to the 1 minus 1/4. Because if we're dividing like bases, we subtract the exponents. Well, 1 minus 1/4 is 3/4. And that's it. If the exponent's negative, there's other things we would do, but at this point, we're not going to have that. And if you want to check these, you can. And make sure you got it right, because we could put 3 over 3 to the 1/4 in a calculator. It's going to give you a decimal, which again, we have our answer 2. We can see if the decimal answer from the starting problem matches the decimal answer for our answer. And if they do, they are the same. And we got the right answer. Number 3, 20 to the 1/2 over 5 to the 1/2. Well, they both have the same exponent, yes? And it's 20 divisible by 5. Okay. So to make our calculations a little bit easier, I'm going to move the 1/2 outside because we can pull that away. This is our quotient of a power of a quotient property. 20 over 5, 4. 4 to the 1/2 to the 3rd is 4 to the 3/2. Well, yes. If we do calculate this out, we do get 8. And that seems odd, yes? Now, questions on how we got 4 to the 3/2. Well, and part of where we're getting 8 is we can see it right here, 4 to the 1/2. 4 to the 1/2 is the same as the square root, yes? So we're saying what times itself is 4? Do we have that? 2, yes? Because this here is 2. Still to the 3rd, which is 8. Now again, with some of these here, if you want to check it in a calculator, go from there. At the start, it still works. Now, a different color. Another way we can look at this is 4 is 2 squared, yes? Powers of powers do what? Two times 3/2 is 3. Yes. Which is 6/2, which is 2 to the 3rd, which is indeed 8. I will take either. Now, part of the reason most of the others have not simplified, well, 2 and 3 are both what? A special type of number. Prime. That's as simplified as they get. It's the only factors are 1 and 2. They're not perfect squares. 5 is not a perfect square. 7 is not a perfect square. 6 times 4, 12 is not a perfect square. 4 here is the first one they throw at us, and the first one we look at is actually a perfect square, number times itself. That's the only reason it's simplified, and it's odd they threw it in at that point. Five to the 1/3 times 7 to the 1/4. Powers aren't the same, but we do have a power to a power. Powers of powers multiply. So we'll have 5 to the 1/3 times 3 times 7 to the 1/4 times 3. Powers of powers multiply. Well, 5 to the 1/3 times 3 is just 5 to the 1st, or 5. 7, well, our 1/4 times 3 is 3/4. So we have 5 times 7 to the 3/4. 7 doesn't reduce because it's prime. That's one of the main things. It's not a perfect square. Here we would need a perfect fourth power, a number times itself 4 times. Smallest one is 1, because 2 would be 16. 2 to the fourth is 16. So they get big. Questions on these here? Really, that's it. We do have more to the note sheets, yes? It's just we're doing more of them. That's all we're doing today, okay? The next one's kind of nice. 3 to the 1/2 times 3 to the 3/2. Yes? If we multiply like bases, we add the exponents. When you multiply like bases, we add the exponents. So 1/2 plus 3/2, which is 4/2,
Yes.
which is 2, which is 9. 3 squared is 9. Because if we get a nice number, an integer, you want to simplify it all the way down. But it also means I could have plugged 3/2, 3 to the 1/2 times 3 to the 3/2 into the calculator, and it would have given me 9 to begin with. 7 to the 2/3 times 7 to the 1/2. When we multiply like bases, we add the exponents. Well, 2/3 and 1/2 don't add together as nicely. 2/3 plus 1/2, 7/6. We can let the calculator do that for us. And that's as far as it goes, because we can't take the 6th root of 7 nicely, and since it's not asking us to find the approximate value of this here and around the 2 decimal places, the next section is just continuing on with this here. Because here I want to dip our toes into this, because there are other things that go along with it, and especially with radicals. Here we're just looking at fractional exponents. Now our 10 to the 1/2 over 10 to the 1/4, when we divide like bases, we subtract the exponents. So 1/2 minus 1/4 actually gives us 10 to the 1/4. And that's actually as far as it goes. Because for us to actually have a power of 10 simplified, it would actually have to be 10,000. So the 1/4 would be 10. But we get this here. Questions on this so far? Awesome. If you do have questions, please ask. 4 to the 3/2 squared, powers of powers, multiplies. So we're saying 3/2 times 2, which is 3, which actually did simplify nicely. Questions on this here? We feel good with these here. Oh. Yeah. I'll look back at these just to make sure. Yep. Yep. Yeah. Yeah.
3 weeks.
Because 8, yeah, because this is going to be 1/8. 27, or B, is the only one that works a little, not different. You good? 27 to the 1/3. Is there a number times itself 3 times that gives us 27? Yeah. That's the only real difference on that one. That we can actually take it to the 1/3 power. We can take the cubed root of it. And then we square it. So it'd be 3 squared times 6 to the 1/4 times 2. 3 squared is 9. So we square it because of our power of 2 on the outside. Yeah. Now, 3 squared, we can simplify because that's 3 times 3, which gives us 9. We wouldn't do it with the 6 to the 1/2 because we can't take the square root of 6 and get a nice number. So we call it good there. And yes, this can be a little confusing at times because it seems like for some we're simplifying, some we're not. Some we're doing this, some we're not. And essentially we're trying to, yes. And depending on which one you see first, go with it. Yes. Now luckily we are doing 3 through 10. Yep. So 3 through 10. So 25 to the negative 1/2.